Hello. Today we are gonna to go over two problems about how to do shear and torsion. So the first problem that we are going to work on is a irregular shaped rod. So this is the rod geometry, and first it is a cylindrical. It has a cylindrical section, and then it has a hollow section in the end. So let's say this distance is a. So the rod has three parts with each part with length of a, and then this diameter is 4d, and then this point is A, B, C, and D. So this diameter is 2D, and then this diameter is just D. So and it experiences a torsion to the left, T0 at point B, and then a torsion to the left at point C, and then a torsion to the right with a value of 2T0. So the problem asks us to find the location and value of the maximum shear stress in the bar and the rotation at point C and D. So find find tau mass and phi C and phi D. That's our problem. So let's work on the first one first. To find the maximum shear stress, we need to look at these three different segments. So the first thing we need to do is to draw a free body diagram. So let's call this unknown TA, so torsion at point A. So we can write a equilibrium equation. So we have TA plus T0 plus T0 is equal to 2T0. From that, we can find out TA is actually equal to 0, right? So which means there is no shear between the rod segment A and B. So A and B, let's write down. So tau A and B is equal to 0 because TA is equal to 0. Okay, so now let's look at the rod segment B and C. So if that's B and this is A, let's call this tau B, C, and then we know that this is T0. So we know from equilibrium equation we have TBC is actually equal to T0. So we know the equation for tau shear stress tau is actually equal to TBC times the diameter, times the radius over IP, right? So the radius is D, right? I will just change it to T0 here. And then IP for a circular rod is so we know that IP is equal to pi r to the 4th over 2, right? So in this case, r is D, so IP we have pi d to the 4 divided by 2, which is just multiplied by 2. So the final answer we have is 2T0 over pi d to the cube. So that's the shear stress for the rod segment B and C. And let's look at C and D. So as we can remember, C and D is a section like that. So this is 2 tau 0, and then this is D, and then let's call this TCD. So from equilibrium equation, we have TCD is equal to 2T0. And then so we can apply the same equation. So shear at CD between CD is equal to 2T0 times R, which is D again, and then over IP. So IP for a hollow section is pi over 32 times the outer diameter, which is 2D square minus, to the 4th minus the inner diameter. So this is IP, inner diameter to the 4th minus, outer diameter to the 4th power minus the inner diameter to the 4th power. So when we simplify this down, we have 15 pi e to the 4th over 4, over 32. So let's plug these things. 15 pi e to the 4th divided by 32 is just equal to multiplied by 32 here. So when we simplify this down, we have 64 T0, 15 pi e to the cube. So as we can see, the maximum shear stress occurred between the rod segment C and D, because the first one, tau BC that we calculate is 2T0 over pi d cubed, and then tau CD is equal to 64 T0 over 15 pi d cubed, so it's larger than 2T0 pi d cubed, right? So we know the mass shear stress is equal to 64 pi T0 over 15 pi e cubed, and it is in the section of the rod CD. So with that, we answer the first part of the question. So the second part of the question asks us to find phi C and phi D, right? So let's draw this again. So this is A, and A. Tells T0, T0, and 2T0. So we know that the rotation for a bar segment is equal to T times length divided by GIP, right? So A, B, C, and D. So we know the section AB do not have any torque. So phi AB is also 0 because TAB is equal to 0. So phi C is just equal to phi BC, right? And then which is equal to TBC times A divided by GIP. And then TBC we calculated to be T0 times A. GIP we already got it from the previous problem, which is pi d 4 over 2. And then simplify this down, we will have 2T0A divided by G pi d to the 4th, right? So this is phi C. And then, so phi D is just equal to phi C plus phi CD, right? And then this one we already got. And then this part is just, okay, so phi CD is just equal to TCD times A divided by GIP, right? And then TCD we calculated to be 2T0. A is a parameter that we already know. G is given. IP is 15 pi d4 over 32. So when we simplify this down, we have 64 T0A 15 G pi G pi d to the 4th. So when we add this together, let me say 15 here. So when we add them together, we have 94 over 15 pi, and then T0A divided by G d to the 4th. So with that, we solved the question. So now let's move on to the next question. So the next question is a rotational problem. So this is a circular rod A, B, and C. So at point B, there is a support on both sides, and then the rod is experiencing a torsion T0, and then there's a small gap between this rod and the support with distance s. So if you look at it from the sideway, then this is the rod that we are talking about, and then this is the support, and this distance is s, and this distance is also s. So the problem asks, and we are given GIP. So GIP is given. So the first question, we need to find TC such that this rod barely closed the gap. So in order to close the gap, it means this torsion treats the rods such that I will just call these two being hit the support here, like barely hit the support. So let me demonstrate it here. So it's just like this. So it treats it such that these two being hit the support. So we have to relate S to phi, right? Let's call it phi B, because that's the only way that we can solve the problem. So what's the relationship between phi B and S? So let's think about it this way. Phi is the angle and S is a length, and this distance is B. So we have S over B is equal to tangent theta B, right? But we know theta B is a really small angle because you cannot trace a bar, like rotate it in a really large angle. So we can say S over B is actually equal to the value of phi B. So okay, so now we know S, we know B, and then how do we get phi B? So in order to get phi B, we have to look at the rod itself. So because the beam barely hit the support, which means there is no force generated on the in the both end of the beam. So let's call it TA, the reaction torsion at point A. So we have TA is actually equal to T0, right? So let's call this distance 2L and this distance L. So we know phi B is just equal to TA times 2L divided by GIP, right? And then we know that phi B is equal, so TC is what we are trying to find, so I will just change it to TC. So we have TC 2L GIP, which is equal to S over B. So when we change this around and simplify everything, then we will have so we are going to isolate TC. So TC is actually equal to GIP times S divided by 2L times B. So this is the critical torsion such that it will close the gap. So that's part A, and then part B asks. Part B asks, when you apply a torque T0 that is greater than TC, what is VC? So when you apply a torsion greater than the critical torque, A, B, and C, what is VC? So we know when you apply a torque that is larger than critical torque, then this two beam will hit the support and then it will generate a force like that, and it is like a negative torque to the beam. It's like applying a negative torque to the beam. So this is, let's just call it T, and we know that T is just equal to, so let's call this F, this is B, so the torque is just F times B, and there are two of them, so 2FB. So this is TA. So okay. Okay, so let's find TA first. So we know TA plus T is equal to T0, right? And then we know that phi B is fixed, right? Phi B is fixed, which is equal to S over B. And then with that we know that, okay, so this is TA, this is TAB. So we know that TAB is equal to TA, and also TAB times the distance 2L over GIP is equal to S over B, which is phi B, right? So with that, we find out TA is equal to TAB is equal to GIPS over 2BL. So looking at this expression, we know that the value of TA will not change no matter how you change T0, which means no matter how hard you twist the rod, the section AB will not have like any changes. So that tells us something, which is phi B is fixed, and it is equal to S over B. So to find phi C, we need to find phi B and then just plus add to plus phi BC, right? So we already know phi B is S over B, and then phi BC. So let's say this is the section T0, this is C, and this is TBC. So we know TBC is just equal to T0, right? And then this distance is L, and then GIP is phys. So this is the new phys. So I think the only trick to this question is phi B is phys, and then phi C is just depends on how hard you twist T0. So I mean how hard you twist the rod. So if you increase T0, this part of the equation will increase, and then but S over B, which is the part come from the rod section AB, will not change. Okay, so with that we solved both the problem. Thank you so much for listening. Feel free to email me if you have any question.